The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
We're going to talk about inclusion-exclusion, which is a generalization of what we did at the end of last lecture, which was about the sum rule. Everybody's still talking, I hear. Anyway, the inclusion-exclusion principle is very important, and the best way to explain this is by using Venn diagrams. So let's do this. So what did we do before? When we worked on the sum rule, we saw that if we count the union of a whole collection of sets that are all disjoint, then we can just sum all the cardinalities of each of the members. So in the case where we have intersections, so sets are not disjoint, well, if you just count all the cardinalities, all the sizes of the sets together, you will start to do some double counting. So with the inclusion-exclusion principle, we can actually exactly compute the cardinality of the union of sets. And you will see that this principle can be used in plenty of examples, including some of them that are on the problem set. So how does it work? So let's take an example where we just have two sets and they have an intersection. So say this is one set, which we call M, and say here is another set, which we call E. Well, they have an intersection, there's some overlap over here. So if we would like to write out the different areas over here, what are they equal to? Well, this is everything that is in M, but we exclude what is in E. So we write that M\E. This part over here is the intersection of, this may be a little bit too small. So this is the intersection of both sets. And over here we have everything that's in E, but excluding what is in M. So if you just write out the cardinalities of the different sets that we are interested in, so we would like to compute the cardinality of the union of M and E. So let's have a look how the cardinality of M itself can be computed. Well, if we use the sum rule, which says that we can simply add the two disjoint sets that make up set M, we can count each of those cardinalities. So we have M consisting of this part, which is M excluding E, plus the part that is right here, which is the intersection. So we use the sum rule and conclude that we have the sum of everything that's in M excluding E plus the cardinality of the intersection. Now for set E we can do something completely similar. So we will have everything that's in E excluding what is in M. And then we still have the intersection. Now we are interested in the union of the sets M and E. And now we need to add this one, and this one together. So what do we see? We see that this is actually equal to everything that is in M but not in E, everything that is in their intersection, plus everything that's in E but not in M. So we have these equations that we can directly derive from the sum rule. And, well, now we can see here that if we are going to simply add, that's what the sum rule would say, simply add the cardinality of M and of E. Well, if we add those two together, we will count the intersection double. So we'll need to cancel that because it's only counted once in the union. So if we combine those three over here, those three equations, then we can conclude that this counts the set M intersecting with E twice. So we have that the union is really equal to the cardinality of M plus that of E minus their intersection. Now we can generalize this, and we will give one more example where we have three sets, and then we'll give the general equation. So suppose we have three sets now, like one, another one, and another one over here. So we have M, E, and say the set S. Well, let's have a look how many times these different areas that are all disjoint, how many times they are counted when we add the three cardinalities together. So we have M plus the cardinality of E plus the cardinality of S. Well, if you do that, then we count this area exactly once because it's in M. This area we count once because it's in M, and another time because it's in E, so it's twice. This particular area is only counted once in this sum over here. And similarly, we have 2 times over here, 2 times here, and 1 times over here. And this intersection of all of the three, well, it's counted when we count elements in M, but also when we count elements in E, and also when we count elements in S. So this is counted 3 times. So, well, let's have a look. It seems like we want to do exactly the same as what we did before. We like to subtract the intersection of M and S. That's this part that cancels the double counting in this area, right? We can subtract this intersection such that this part is cancelled, like the double counting here is cancelled. And similarly, we want to subtract the intersection between E and S, which would eliminate this double counting. But now we can see that we start to subtract too much, because this central area here will be, well, it's part of each of those intersections, so it's actually eliminated. All of it is subtracted. So let's create the same diagram, but now when we count the sum of all those intersections. So we have the intersection of M intersect with E, the intersection of M with S, and we also want to figure out how many times elements are counted in the set E intersect with S. So let's have a look. Well, this area here is counted 0 times. It's not part of any of these intersections because this part is only in M and not in S or E. So this is counted 0 times. And here we have the same. Well, this part over here is exactly once in this intersection between those two sets. It's not in this one, so this is counted once. So we have by symmetry that for all the others. This area, however, is in both this intersection as well as this one and also this one, so it's counted 3 times. So now we can easily start to combine all these together, and you can see if we take this sum and we subtract this, then the middle area is cancelled, so we have to still add the intersection of the 3 sets, the intersection of M, E, and S together. So in the formula, that would look like this. So we are interested in the union, and this can now be written as, well, the sum of the cardinalities of the individual sets, and we subtract the intersections that we have up there. So M intersect E minus M intersect with S and minus E intersect with S. Now we have eliminated, if you look at this Venn diagram over here, this diagram over here, we have eliminated everything that's in the middle area. So we still need to add the intersection, everything that is counted in the intersection of M, E, as well as S. So we have this equation, and now you can see why we call this the inclusion-exclusion principle. Here we include all the elements in M, E, and S. Now we have to exclude what we counted too much. So we have exclusion over here. And now we again have to include some stuff because, you know, we excluded too much. And then we keep on going like this. So in general, we get the following theorem that says that if we look at the cardinalities of the cardinality of the union of a whole bunch of sets, say we have n sets, then this is actually equal to, well, we first include the sums of all the individual cardinalities, so which is I from I equals 1 to n, cardinality of AI, minus, now we have to, again we have to eliminate all the double counting, so we look at every pair of sets indexed by I1 and I2, and we look at their intersection, and we take that out using this minus sign, we exclude this. And we continue like this, so we add now, because we have excluded too much, we have to include some more. We look at all triples of sets, indexed by I1, I2, and I3. And now we look at the intersection of those sets. And we continue like this all the way till we look at the very last intersection that you can have, which is intersection of all the sets. And it depends on whether n is even or odd, whether we have to include it or exclude it. So we have a minus 1 to the power n plus 1. And then we have the intersection of all of these. Now we can write this out in a more elegant formula, where we just put all this, what I wrote here, in a sum. And then it looks like this. It's the sum over k equals 1 to n, minus 1 to the power k plus 1. So depends whether k is even or odd, whether we do an inclusion or an exclusion in the sum. And we look at all the subsets that are subsets of the index set 1 up to n, such that the cardinality of the set S is equal to k. And now we need to look at the cardinality of all of the intersection of all the sets that are indexed by S. So that's, so I put I, so do the intersection over all I in S of the sets AI. So this general formula is the inclusion-exclusion principle. And this is the way how you can think about it, how to derive it. Of course, this is not a proof, but you could do this yourself by using induction, and you can use induction on n. So that's a pretty straightforward exercise. Okay, so let's give an example. Let's do that over here. You will have a problem that's similar on a problem set. And it goes like this. We would like to know how many permutations are there with a special property. So how many permutations do I have of the set 0, 1, all the way up to 9, so all the all the digits, and that have consecutive, so I put this between brackets just to clarify. So consecutive either a 4 and a 2 right next to one another. So remember, a permutation is a sequence that has each of those digits exactly once. And I like to count those permutations that have a 4 and a 2 next to one another in this way. So we have 4, 2, or the permutation may have a 0, 4, or a 6, 0. So I'm very curious, how many permutations do I have? And I'm going to use this principle that I just described. So how do we need to go ahead with this? So, so I'm interested in the permutations that have 4 and 2 next to one another. So that could be my first set, say M. And then I have a set that I want to count that has the 0 and the 4 next to one another. That could be my E. And the S could be those permutations that have the 6 and the 0 next to one another. So then I would like to use that rule over here. So I would also need to count all the intersections and so on. So let's do this. Let me first give an example of such a permutation. So, for example, I could have the permutation that is the sequence 7, 2, 5, 6, 0, and the 4, for example, 3, 5, 1, and 9. So I have all the digits that are contained in the set, and I see that actually this particular permutation has a 6 and a 0 next to one another, so it's in this particular, the set of permutations that have a 6 and a 0. I can also see it has a 0 and a 4, so it's also in the set of permutations that have a 0 and a 4 next to one another. Okay, so now I'm going to define these different sets, and then we're going to start counting these. And this is the type of counting that you're doing in this problem set, and the intuition that you create by doing that, you can use later on when we study probability theory. Okay, so let's define the set P42 as all the permutations that have, so it's the set of permutations with 4, 2. And similarly, we have P04, which is the same thing, but now with 0, 4. P60, the set of all permutations with 6, 0. So let's have a look at what the size is of an individual set of permutations. How can we do this? So let's have a look at the size of, say, this one, P60. Well, what kind of trick can I do in order to count this? So we have learned a few rules last time, and what I would like to do is, well, this is a slightly more complex structure, so I would like to map this to a set by means of a bijection. That would be great. Then to some kind of other set that is easy to count for me. So then, by the bijection rule, I will be able to figure out what the cardinality is of this set. So the trick here is to find such a bijection, and the idea is that you could actually treat the 6 and the 0 as one unique symbol. So let's see how it works. So what I could do is I can have from the set of from P60, so all the permutations that have 6 and a 0 next to one another, I can find a bijection to the permutations of the set that have 6, 0 as a single symbol, and then I have all the other symbols, all the other digits, so 1, 2, 3, 4, 5, 7, 8, and 9. So let's have an example of, we have one up here actually. So how would I map this? This would be mapped according to that definition to 7, 2, 5. And now I combine 6 and 0 into one symbol in my sequence. And then I have the rest, 4, 3, 5, 1, and 9. Now this is easy for me to count, right? So this is a bijection. And by the bijection rule, the cardinality of this set is equal to the total number of permutations on this set. Now this set has exactly 8 elements, so I know how many there are. So I know that the cardinality is equal to 8 factorial, because there are 8 factorial permutations on sets of size 8. We saw that last time. So that's the trick. Or, oh, is it 9? Oh yeah, you're right. Great. So this is 9. And similarly, in the same way, we can also count these, right? We can treat 0, 4 as one symbol, or 4, 2 as one symbol. So I also know that the cardinalities of these are also equal to 9 factorial. Now when I use the inclusion-exclusion principle, so now I've computed those 3 essentially, I need to subtract their intersections. So let's compute the intersections. And if you do that, we're going to use the exact same trick. So we're going to find a bijection to permutations of a set of symbols. And we just have to specify those. So let's do this together and take, for example, the intersection of P42 with P60. So what kind of a bijection could I have? So it will be all the permutations on what kind of a set? So I use the exact same trick here. So I'm going to treat 4 and 2 as one symbol and 6, 0 as one symbol. So I have 4, 2, 6, 0, and then all the other digits. So it's the 1, 3, 5, 7, 8, and 9. You can count that this number is 8. So by the bijection rule, we have that the cardinality of this intersection is equal to 8 factorial. And we continue like this to compute all the other intersections, and they do look a little bit different sometimes. So for example, if I have 6, 0 and P04, so let me define the permutation first, or the bijection first. So how do I do this one? Any suggestions? So what kind of a set can I find a permutation to? If I look, so over here I have a permutation in which 6 and 0 are next to one another. But this is also a permutation in which 0 and 4 are next to one another. Yeah, exactly. So treat 6, 0, and 4 as one symbol, because a permutation that's right in here has a 6 and a 0 next to one another, and the 0 should also be next to the 4, because it's in this set as well. So we know that every permutation in here has a subsequence of 6, 0, 4, like next to one another. So we can treat this as one symbol, and then we have all the other ones. And again, these are 8 elements. So we have that also for this intersection, the cardinality is equal by the bijection rule as the total number of permutations on a set of 8 elements, which is 8 factorial. So for the last one, we also have a similar. Let me see which one I need to do. So I have 4, 2 and 0, 4. Well, again, I do the same trick. Now I have a symbol that has, well, the permutation in here has a 0 and a 4 next to one another, and the 4 is next to one to a 2. So I treat this as one symbol. So if the permutations on the set 0, 4, 2, and then 1, 3, 5, 7, and 6 as well, 8, and 9. So the cardinality of this set is also equal to 8 factorial. So now we still have to look at the intersection of all of those three in order to use the inclusion-exclusion principle. And well, the same trick can be used over here. So we look at the intersection of P60 with P04 and the permutations that have 4 and 2 next to one another. So what does that mean? It means that the permutation that's in here has a 6, 0, and then a 4, and then a 2. So these are all the permutations with a 6, 0, 4, 2 next to one another. And this can map easily to the set where we treat this as one symbol, 6, 0, 4, 2. And then we have 1, 3, 5, 7, 8, and 9. This set has 7 elements. So the intersection of these three is equal to 7 factorial. Now we can use the inclusion-exclusion principle using this over here. And when we plug everything in here, we can see that the intersection, that the union, that when we count the union of P60 with P04 and P42, it's actually equal to 9 factorial for these, 8 factorials for those, and a 7 factorial for these. So it's 3 times 9 factorial minus 3 times 8 factorial plus 1 times a 7 factorial. So this is how we can use the inclusion-exclusion principle. So this generalizes the sum rule, and now we have a whole set of rules already discussed since last time. We continue with the bookkeeper rule. You have already seen it during recitation, so I will only write it out once more. And all these rules together we will then use in a set of examples. So what was the bookkeeper rule? We have that so the bookkeeper rule is if I have distinct copies of letters, so distinct copies of letters L1, L2, L3, and LK, well then the number of sequences that have exactly n1 letters of the type L1 and n2 letters of the type L2 and so on, well we can count those. So sequences with n1 copies of L1 and n2 copies of L2, and then we continue like this until we have nk copies of LK. Well, we can count this. So these copies can be in an arbitrary order in the sequence, and we saw in recitation that this can be written as n plus 1 plus n2 all the way up to nk factorial, and we divide out the product that starts with n1 factorial times n2 factorial up to nk factorial. And this we also can write as what, well, this is actually the definition of what we call the multinomial coefficient. So you've already seen the binomial coefficients, and which is a special case of this one. So we write this as n1 plus up to nk, and then we have n1, n2, and we just repeat all of those in here. If we have k equals 2, then we get the binomial coefficient. And if k equals is 2, we also often just forget about the last term. So we would get expressions that look like this, which is really equal to n k, comma, n minus k. Okay, so this is some, these are some definitions. And we can apply this bookkeeper rule. For example, last time in the lecture we were talking about the number of bit sequences of length 16 with 4 ones. We wanted to count these because we found out that if we want to select 12 donuts of 5 varieties, we can find a mapping, a bijection, towards this set of bit sequences with 12 zeros and 4 ones. So the bookkeeper rule will tell us exactly how many there are. And that's the most basic example, essentially, of this way of counting. So what do we have? So the number of bit sequences of length 16 and with 4 ones, well, it's exactly equal to, according to this rule, as length 16, and we need to choose 4 ones out of these 16, and that's the binomial coefficients, where we choose 4 out of the 16 symbols. And this is equal to 16 factorial divided by 4 factorial times 12 factorial. Now we often also denote this, the following rule. We sort of identify as a special case. We say that the number of k elements subsets of an n element set is actually equal to n choose k. So this is an important rule to remember, which will occur many times. Okay, a theorem that we can have derived from all this stuff is what we call the binomial theorem. So we'll quickly go over that. The binomial theorem says that for all integers n, positive integers n, we have that a plus b to the power n equals to the sum where we take k from 0 to n, and then we have the binomial where we have this expression over here. We choose k out of n, and we choose, say, k times b in this expression. I will explain in a moment by an example, and n minus k a's. And this is the theorem, and I will just give an example just to show how we can think about this. So let me do that over here. So if we take n equals 2, then we can see that we get all the combinations, essentially, of a and b of length 2. So you have a times a times b times a, and b times b. So what do we see? We see a square plus ab plus ba plus b square. Now we see that these have 1 times an a and 1 times a b. This one has 2 times an a, and this one has 2 times a b. And this combines together as a square plus 2 times ab plus b square. Now if you have n equals 3, so we have a plus b to the power 3, we will get all the different products, all the different terms that add up to this, are all the kinds of combinations of a's and b's. So for example, we have 3 a's, so 3 times a, but I can also have a squared times b plus aba plus ba squared, and those have exactly 2 times an a and 1 times a b. I can look at all the others, so I may have 2 times a b and 1 times a, So what are those? We have a times b squared plus ab plus b squared a. So I count these as the same, right? They each have the same number of b's, 2 times a b and 1 times a. And then finally, I have b to the power 3, which counts 3 times a b. So these are all the possible terms that I have. There are 8 in total, 1, 2, 3, 4, 5, up to 8. And that fits, right? Because I can have a choice of an a and a b, and I do that 3 times. So 2 times 2 times 2 is equal to 8. So I have 8 terms, and I can group them together by taking a to the power 3 plus 3 times a square b plus 3 times, and now I have b square a, and finally b to the power 3. So what do we see here? How many terms are there that have exactly 2 times an a and 1 times a b? Well, it's like we have a set of 3 elements, right? And or 3 positions. And I like 2 of them to be in A. So I choose 2 out of those 3 to be in A. So I use this subset rule to count how many times I see the same term back. So let's write this out. So that is that, so the number of terms that have k times an a, and we have, say, n minus k times a b. Well, how many terms do I have? Well, that is the length of, so the number of, oops, let me change that. So it's the number of length n sequences that have the following property, that these have k a's and n minus k b's. And that's easy to count, which is equal to what we have done here before. And we have the binomial n choose k. And that, if we plug that in over here, then we get this particular sum. So this is the binomial theorem, very famous. And now we're going to use all this stuff to count some poker hands. So we have come to this part of the lecture. So we're going to do a bunch of examples that are similar to some of those that you will see in the problem set. And then at the end we go and continue with a different proof technique. So let's first define a deck of cards, because that's what we are going to use now. So for this type of problems, we will use a deck, which is actually a set of 52 cards. And a card itself actually has a suit. And the suit can be something that looks like this, which is called spades, S of spades. We have another symbol, which is this, hearts. And we will have clubs, and we have diamonds. And besides a suit, a card also has a value. And the values are range from 2, 3, 4, all the way up to 10. Then we have a special symbol, special value, which is called the jack. We got a queen and a king, and finally the ace. And in total, we have 13 possible values. So you can see that we have 4 times, because we have 4 different suits, 4 times 13 is 52 different cards, and that makes up a deck. So we're going to look at hands, and a hand is actually a collection, or a set of 5 cards. So it's a subset of the deck. of 5 cards. And we do not worry about the order of the cards in your hand. They can be permuted if you want to, so the order is not important. So it's a subset of 5 cards. So how many hands do I have? Well, how many ways are there to choose a subset of 5 cards out of a deck of 52 cards? Well, we can use a subset rule, and we get the binomial 52 choose 5. Which is, by the way, a lot. So let me write it out as well. It's about 2.5 million. So we are interested in, when we play poker, well, if you do that, in really good hands. So we like 4 of a kind, which means that we have 4 cards that actually have the same value. Or we have cards that, hands that have what we call a full house. We will count those in a moment. Or other kinds of combinations. And the rarer the combination is in your hand, the higher or the better your hand is, and the more likely it is that you win the poker game if you do not get left out. All right, so let's give an example of 4 of a kind. So we're going to compute those, and we will see that we need to use a combination of all these rules. Okay. So 4 of a kind is the special hand where we have 4 of one kind of value. Notice, by the way, that the 5th card, because of this, must have a different value, right? Because there are only 4 cards that have, say, the value 8, because there are only 4 different suits. So the 5th card will automatically have a different value. So as an example, we will have the 8 of spades, and then the 9 of diamonds, and all the other 8s, the 8 of diamonds and the 8 of hearts, and say the 8 of clubs. And how do we count these types of hands? We're going to look for a representation of how can we represent such hands, such objects. So we have to count a special type of object, a special kind of poker hand, and in order to do that, we're going to look for a way to represent these objects, and then in such a way that we can count them very easily. And that's really the trick in order to solve these kinds of counting problems. So the representation that we have here is, well, we can choose, first of all, we can choose the value of the 4 kinds, of the 4 cards. So how many choices do I have? Well, I got any choice. There are 13 different values, so I have 13 choices, so that's easy. Secondly, I can choose the value of the extra card. So how many choices do I have here? Well, the 4 of a kind already eliminates one kind of value completely, right? So I have any of the other values is possible, is equally likely even. So I have 12 choices. And lastly, I need to still represent the suit of the extra card. So I also want to know the suit of the extra card. And how many choices do I have? Well, I can choose any of those 4. So that's 4. So essentially what we constructed here is a mapping by using this representation. And the mapping tells us is as follows. Let's keep this up. So the mapping goes from poker hands, or from from hands to from hands with 4 of a kind to this representation. So let's write it out. So we have 4 of a kind, and then we have a function, a mapping f, that goes to this representation. We will have the first entry, the value 1, and the value 2, and then the value 3. So for example, if we take this hands of cards, well, the first one, we see that the 4 of a kind has value 8. The value of the second card is the 9 of the 9 diamonds card. So I have a 9. And finally, the suit that I need to select for the extra card is diamonds. So this is an example. And now we know, because this is a bijection, we know that the number of hands with 4 of a kind is equal to all these types of sequences, that are chosen according to this representation. So, well, we have 13 choices for the first value, and given this first value, we have 12 choices for the second value, and given those two, I have 4 choices for the very last entry in this sequence. So this is the generalized product rule that I'm using. So we see that the number of sequences is equal to 13 times 12 times 4. Turns out this is equal to 624. Well, if you divide it over the total number of cards. So how did we do this? This is the generalized product rule. If we divided this number over the total number of cards, we get a fraction of 1 over about 4,000. So it's really rare that you get 4 of a kind. So it's a really good hand. Okay, let's do a few more of these. We also like to know how many full houses there are. A full house is a special hand. It has 3 cards of one value and 2 cards of another value. So how many are there? So again, we're going to use the exact same principle. We're going to find a representation of this type of hand. So we have 3 cards of one value and 2 cards of another. So for example, we may have the hand that contains, say, 3 cards with value 2, a 2 clubs, a 2 spades, and also a 2 diamonds, and say a jack club and a jack of diamonds. And another example could be, say, a 5 of diamonds and a 5 of hearts, 5 of clubs, 7 of hearts, and also a 7 of club. So now you can see that it's very easy to represent this, right? We can, we can start grouping things together. We can say represent this by first taking the value of the 3 cards that I have here. So it's 2. Then I want to indicate in a second term in my sequence, in my representation, which suits did I use over here? Well, I used club, spades, and diamonds. So it's the set club, spades, and diamond. And now I also have a pair, like 2 cards with the same value. What's the value? It's jack. And what are the suits associated to these? Well, it's the clubs and the diamonds. So I've not yet given you the formal definition of the representation, but you can see that you could do something like this. So that's often how we start out on a piece of paper. You try to do something, and hopefully it works. So we have here we have diamonds, hearts, and clubs. And then we have, finally, we have two cards with the same value, 7, and they have the hearts and clubs as suits. Okay, so the representation is defined as follows. We just started out with a first entry in my representation, and this is going to be the value of the triple. So how many choices do I have for this value? Well, I can choose any of the 13 possible values. So I have 13 choices. And the second part is the suits of the triple. Well, I have to choose a subset of the 4 possible suits of size 3. So I need to have a subset of size 3 out of the 4 possible suits. And that will give me the proper representation. So how many choices do I have for such a subset? Well, there's 3 elements out of 4. So we can use the subset rule and see that this has 4 choose 3 equals 4 choices. Then the last part is the value of the pair that I have, of the 2 cards that are having the same value. Now, how many choices do I have here? Well, I have to be a little bit careful, though. I just want to make sure that I do the right reasoning here. I know that there's still, because I chose a triple of cards of the same value. For example, over here, I chose all these 2s, but I still have 1 card in my deck which has a 2. Actually, here I've chosen clubs, spades, and diamonds. So the one that is missing is the 2 of hearts. So could possibly choose the 2 of hearts. But wait a minute, if I choose the 2 of hearts, how can I make a pair? That's not possible, right? Because I've already chosen all the other 2s. So there's no other 2 to match to find a pair. So actually I cannot choose this particular value of this triple for the pair. So, but all the other values are possible. So I have 12 choices, 1 less than the one that I've already chosen for the triple. Now and then similarly, I can choose suits of the pair. And how many choices do I have? Well, look at every possible subset that I can have of size 2 out of the 4 suits. So I use the subset rule and find that this is 4 choose 2, which is equal to 6. So now we're going to multiply all of these together. We use the generalized product rule again. So we have found a mapping from hands with a full house to these types of representations, to this representation. And this mapping is bijective. So the number of full houses is exactly equal to the number of these representations. And by the generalized product rule, I can choose the first entry of such a sequence in 13 ways, the second one, given the first one, in 4 ways. This one I can choose in 12 ways, given I've already chosen my triple, and so on. So by the generalized product rule, I know now that the product of those 4 is equal to the total number of full house hands. So how much is that? It's 13 times 4 choose 3 times 12 times 4 choose 2. And this turns out to be equal to 3,744, which is a factor 6 bigger than a 4 of a kind. So it's much more likely that you get one of those. And that's the reason why 4 of a kind has more worth, is worth much more than a full house. So let's do another example, a hand with 2 pairs. Let's see whether we can continue this type of reasoning. It's going pretty well. And maybe yeah, we can do the same thing. We'll see that in counting you really have to take a lot of care. So maybe you can already see what's happening when I start reasoning in the exact same way as before. So let me first define what I want to count. It's a hand that have exactly 2 pairs. So what does that mean? It means that that we have 2 cards of one value and another 2 cards of another value. So let's start out as before. We're going to write out the representation and see whether we can do this properly. So we're going to use the exact same technique. So first of all, we're going to choose the value of the first pair. Now, how many ways can I do this? Well, I can do this in 13 ways. Any possible value is possible. I need to choose the suits of the first pair. And how many ways can I do this? Well, I use the same technique as over here, so it's any possible way to choose 2 elements out of a set of 4 which represent all the suits. So that's 4, choose 2. Then 3, we're going to choose the value of the second pair. And, well, that's easy because the second pair, by definition, must have a different value than the one in the first pair. Well, I've already chosen one value, so I have 12 choices left. So that's no problem. And now we can continue and do the same thing. So we're going to count the number of suits that are possible for the second pair. And that's the same number as we have for the first pair. So we have number of suits of the second pair. Again, we need to choose 2 suits out of the complete set of suits, which has 4 possibilities. So it's 4, choose 2. And now we can have still a choice for the last card. We have now 2 pairs. We still have a 5th card. The 5th card also has a value. Actually, I did not write it down, but if we talk about the hands with 2 pairs, we mean 2 cards of one value, 2 cards of another value, and the 5th card, the extra card, has yet another value, because otherwise we would have a full house. And we have already counted those. Okay, so value of the extra card. Well, I've chosen already 2 values, the one for the first pair, the one of the second pair, so there are 11 choices left. And finally, I can choose a suit of the extra card. Well, I have 1 out of 4 choices for my suit. So, again, we can use the generalized product rule, and we can say that we have 13 choices for my first entry in my presentation, right? For the first choice. Then, given the first choice, I have 4, choose 2 choices for the second, and then 12 choices for the third, if I've already chosen the first 2, and so on. So I can use a generalized product rule and count these representations. So the number of representations is actually equal to 13 times 4, choose 2, times 12 times 4 choose 2 again times 11 times 4 choose 1. So is this the number of the hands with 2 pairs? So this seems to be pretty reasonable, but can you see like something that has happened here that we also saw actually last lecture? Like do I know for sure that the hands with 2 pairs well, that there are this number of hands with 2 pairs? What do I need to check in order to make sure that that is true? Well, I need to I need to prove essentially that this representation is actually a bijection from the hands with 2 pairs to these types of sequences. So is that true? Or does this mapping have a different property? Any ideas? Yeah, over there? No, you don't want to answer? Okay. Well, let me. When we talked about the chess game last time, with the rooks, we essentially had 2 rooks that we could choose, and put them on different positions with no shared rows or shared columns. And here we have sort of 2 pairs with no shared with no shared values. But what can we do? We can actually interchange the first and the second pair. So, as an example, we can have 2 representations that map to the same hand. So let me give an example. So for example, suppose I choose the value 3 for the first pair, and then I'm choosing the set diamonds and clubs for the suits of those. And say the second pair is a queen of diamonds and hearts. And finally I have an ace of clubs. Well, this will be a proper sequence according to this representation. But this maps to a hand that is also mapped to if we interchange the first and the second pair. We can also start off with the queen for the first pair. And we have a diamonds and a hearts. And we have a 3 for the second pair with diamonds and clubs. And then we finally have the 5th card, which is the same, the ace of clubs. Now these map to exactly the same hand. We just interchange the first and the second pair. Now this is a kind of a problem, or like a mental sort of confusion that may very easily happen. This is a rather easy example where you can see it, but if you do counting, we really have to take care that we make sure that each of the sequences that in this representation are really represented by, say, one hand, in this case with 2 pairs. Now, but how can we remedy this? It turns out that we can, by interchanging these 2 pairs, these 2 sequences are the only 2 sequences that map to the same hand. So we know that this is not a bijection, but it's a 2-to-1 mapping. So now we can choose, we can use the division rule, and by the division rule, we now know that the number of hands with 2 pairs is actually equal to this whole thing over here, divided by 2, because we have a 2-to-1 function. Now this is really something that is pretty disturbing, because we have a near miss in our reasoning. And therefore, it is important to keep in mind the following guidelines when we do counting. It's always, it's very important to first of all check whether it's truly a bijection, and you need to know how many sequences are mapped to the same hand. So the guidelines are as follows. They're pretty straightforward, actually. First of all, if we have a function f that maps from A to B, then we would really like to check very carefully whether the number, what is the number of elements of A that are mapped to each element of B. So we check how many to one of a mapping this really is. And after this, we will then apply the division rule. It's very important to check this. But very often, we're making mistakes. For example, right now I'm doing some research and I've been counting something. It turns out that if I use a different method to count the same thing, I get a different answer. So I made a mistake somewhere. So that's the second guideline. So what you want to do is you want to try solving a problem in multiple ways. So try solving a problem in a different way. And especially with counting, this is very helpful. So this will lead to an extra check. So we will do that for this particular example. And in general, you would always like to find multiple ways to prove things, I would say, because at least you want to have multiple, maybe not a complete proof, but subparts of proofs. You may want to find different ways why that is true. So that's how I usually do my proving of things. So let's find a second way to count this over here, to do the double check. So we're going to create a different representation that should actually lead to a bijection. So I want to find a representation that's a bijection, a one-to-one mapping. So how do I do this? I can let me see where I am. Okay, so what I could do is, first of all, I can choose the values of the two pairs. So in this case, I have the values 3 and the queen. So how many choices do I have? Well, I can choose 2 out of 13 choices. Secondly, I'm going to describe the suit of the smaller pair, which is uniquely defined because they have 2 values. One is smaller, and the suit of the smaller pair I can choose by taking 1 out of 4, 2 out of 4 choices, because I need to choose 2 suits for the smaller pair. For the larger pair, I do the same. And I get 4, choose 2. Now again I have the value of the extra card. And I have 11 choices. I've already chosen 2, so there are 11 choices left. And finally, the suit for the extra card can be done in 4 choose 1 ways. So if we multiply those together, we get 13 times 12 divided by 2, and then we get times 4 choose 2 times 4 choose 2 times 11 times 4 choose 1, and we can see that that's exactly the same as this whole product divided by 2. We actually have a bijection. This particular representation is a one-to-one mapping. So it's always good to find a second way to prove the same result. Okay, let me do one more. let's do that over here. Just to make sure that we really understand this stuff, I'm going to count hands that have each suit in it. So I want to count the hands with every suit. So as an example, I can have say the 7 of diamonds, the king of clubs, the 3 of diamonds, the ace of hearts, and the 2 of spades. Why is this a proper hand? Because I can see the diamonds, the clubs, the hearts, and the spades. So I have a hand in which every suit is represented. So what do I do for my representation? Well, I can have the values of each suit. And I assign a specific order to those. So I want to represent for the diamonds and the clubs and the heart and the spades. I want to find out what values do I really have. So values of each suit in the order D, C, A, hearts and spades. And how many ways do I have? Well, I have 13 values for the 7. I have 13 values for the king for this one over here, for this value. 13 values for that one, and 13 values for this one. So that is pretty straightforward. Now I still have the extra card, and the extra card has a suit, which I can do in 4 ways, because there are 4 choices. And finally, it also has a value. And the value is actually, so how much is this? Can this be 13? Are there 13 values? No, not really, right? Because for each possible given suit that I've chosen, I already chose a value before when I chose a value for the suit that I did over here. So for example, this one cannot be the 7, it has to be something else. There are 12 choices. If I would have chosen a different suit, for example hearts, then I would not be able to choose the ace, because I already have chosen the ace in the first step. So I have 12 possibilities here, so this is not 13. You may want to check that again. So now let's give that representation for this one. So I can have diamonds, clubs. So let's see, in the order of diamonds, clubs. So I have the 7. I have a king. I have, for hearts, I have an ace. For spades, I have a 2. Then I have the suit for the extra card, which is the diamonds. And then a value, which is a 3. Now we are going to check, according to our guidelines, over here, going to check the number of elements that are, the number of sequences that map to the same hand over here. So is this a bijection? It's not, right? So why is this not a bijection? Well, we can also have the following situation where we swap the 3 diamonds and the 7 diamonds around. So we choose the 3 for the diamonds, and then we have the king, the ace, and the 2. Then we have the 5th card, which is also diamonds, but now it's the 7. Well, this one also maps to this particular hand. So we have a 2-to-1 mapping. And we conclude that the total number of hands where every suit is represented is 13 to the power 4 times 4 times 12 by the generalized product rule. And now by the division rule, we have to still divide by 2. So that's the total number. Okay, so now we come to combinatorial proofs. So this is a new proof technique. And what we're going to do is we're going to count a set in 2 different ways. And that will lead to a combinatorial equation. So the whole idea is as follows. So let me give an example first. So for a combinatorial proof, for example, suppose I have n shirts, and I want to keep k, and I want to trash n minus k. So how do I count the number of choices that I have? Well, I can choose out of n, I can choose the k keepers, but I also can count it in a different way. I can also count this as how many ways I can select the trashers. So there are n minus k out of n shirts that I will trash. So there are 2 different ways to count the same choices that I have. So we have an equation over here. And you already know this one because by the definition of the binomial coefficient, we have that this is equal to this. And so it's pretty straightforward. It's equal to this one over here. But the idea is that we're going to count a set in 2 different ways. So another example is where we have the following. We choose a team of k elements, and of k elements out of, oh, actually I'm talking about a team. I was talking about students here. Of k students out of n students. Now, how many ways can I do this? Well, n choose k, right? Well, there's a way to count this differently. I could also say, well, let's first count the total number of ways in which I choose k students that includes Bob. So let's do that. So Bob is one of the students, and if I count the number of teams with Bob, well, how many choices do I have? I choose Bob. I still need to choose k minus 1 students out of the remaining n minus 1 students. I have taken out Bob, so there are n minus 1 students left, and I still need to choose k minus 1 students. Well, the other possibility is that we have teams that in which Bob is not represented. So now we need to choose k students out of all the students minus Bob. So we have n minus 1 choose k. So by the sum rule, we can just add those 2 together, and that should be equal to all the possibilities to choose a team of k students. So what do I see? I see that n minus 1 choose k minus 1 plus n minus 1 choose k should be equal to, well, before I counted it as this, so it should be equal to n choose k. And this is called Pascal's identity. And the general idea is that we do the following. So we are actually counting a set in 2 different ways. That's what we did so far. And when you solve these types of problems, the difficulty is that you will need to define the set S. So usually you get a problem, you need to prove some equation like this. So you define a set S, that's the hard part of it. Then we are going to show that the cardinality of S is some number n, say, in one way. So we have one method to do this by counting. And we will show that S is also equal to some other number. Like in this case, we had one number, and this was my second one. Also by counting. And then we can conclude that n, so we conclude that n equals m. So we're almost done, because I'm going to prove to you a very simple equation using this technique. But it is not as trivial as the one that we saw just now. What we do now is the following. We want to prove a theorem that says that if we sum r is 0 all the way up to n, then if you take the product of the following binomial coefficients and choose r, times 2n choose n minus r, this is equal to 3n choose n. We need to prove this. So we need to find a proper set. So how can we think about it? Well, the idea is that we're probably going to choose n elements out of 3n elements. We're going to do it in a special way. The proof would be as follows. We take S to be all the subsets of n balls chosen from a basket of n red balls and 2n green balls. And this will do the trick. So how do we do this? We are going to first choose the red balls and then the green balls. So let's first count S in the very easy way. Well, I just choose n balls out of a basket of 3 n balls. I don't care how many green or red balls I have, so I have really 3n choose n choices. So this is the number of n element subsets from a 3n element set. So that's easy. Now we can also count it in a different way. We first of all wonder about the number of subsets with exactly r red balls. So how many are there? Well, we choose r red balls, so we have n red balls, so we need to choose r out of those. Now in total, I need to choose n balls, so I still need to choose n minus r balls out of the set of green balls. I have 2n green balls. I'm going to choose n minus r green balls over here. So these are the red balls that I select, and here are the green balls. Now I use the sum rule, and I add all the different possible subsets with 0 red balls, with 1 red ball, 2 red balls, all the way up to n red balls. So essentially I get the sum by the sum rule of r0 all the way up to n, where I count the number of subsets with exactly r red balls. So that means I can choose r out of the n red balls and another n minus r out of the 2n balls, 2n green balls. So now we equate those two together, and that proves the theorem. So the really hard part in this type of proofs is that you need some creativity to find and define that set S and see how that would work. And the way to do that usually is to look at this equation and then say, oh, wait a minute, I'm going to talk about sets because I choose n out of 3n over here, so out of 3n elements, then maybe I can divide up the sets in some kind of specific choice. So tomorrow during recitation you will also see combinatorial proof. Thank you.